Imagine you're in the fastest spaceship ever built. You push the throttle forward, engines roaring, acceleration building. You're going faster and faster, approaching the speed of light. You can feel it. You're almost there. Just a little more power, just a bit more speed, and you'll break through that cosmic barrier. But then, something impossible happens. No matter how much energy you pump into those engines, no matter how powerful your thrust becomes, you can't reach it. The universe itself seems to be conspiring against you, holding you back with an invisible hand. You add more fuel, more power, more energy, and yet the speed of light remains forever out of reach, like a horizon that moves away as you approach it. This isn't a limitation of your spaceship or your technology. This is the universe telling you something fundamental about reality itself. Richard Feynman, one of the greatest physicists who ever lived, spent much of his career explaining this cosmic speed limit, and what he discovered wasn't just about speed. It was about the very fabric of space, time, and existence. The reason you can't outrun light isn't because you're not trying hard enough. It's because the universe has written this rule into the foundation of reality. And today we're going to understand exactly why, using Feynman's revolutionary way of thinking about physics. Why do you think the speed of light is special? Most people assume it's just the fastest thing we've discovered so far, like breaking a speed record. You might think that with better technology, more advanced engines, or some clever physics trick, we could eventually go faster. After all, humans have a history of breaking barriers we once thought impossible. We learned to fly when people said we couldn't. We broke the sound barrier when experts claimed it was a wall no aircraft could penetrate. So why should the speed of light be any different? Here's the thing that most people get wrong about this cosmic speed limit. It's not like the sound barrier. When Chuck Yeager broke the sound barrier in 1947, he didn't break a law of physics. He just overcame an engineering challenge. Sound moves at different speeds through different materials, and there's nothing fundamental stopping you from going faster than sound. But light? Light is different, completely, fundamentally, impossibly different. The speed of light isn't just the fastest speed we've measured. It's not a record waiting to be broken. It's a fundamental constant of the universe itself, woven into the mathematics of space and time. When you try to go faster, you're not fighting against engineering limitations or technological boundaries. You're fighting against the structure of reality. And here's what will blow your mind as we go deeper into this. The reason the universe won't let you outrun light has nothing to do with light itself. Light just happens to be the messenger showing us something profound about how space and time actually work. Let's start with something that seems simple but opens up this entire mystery. Picture a train moving past a station. You're standing on the platform, and your friend is on the train. As the train passes, your friend throws a ball forward inside the train car. From your friend's perspective on the train, the ball moves at, let's say, 10 meters per second. But from your perspective on the platform, the ball speed is the train speed plus the ball speed. If the train is moving at 20 meters per second, you see the ball moving at 30 meters per second. Simple addition. This is how we understood motion for thousands of years, and it works perfectly for everyday speeds. This is called Galilean relativity, named after Galileo Galilei, who worked out these principles in the early 1600s. Galileo was trying to defend Copernicus's idea that the Earth moves around the sun, and people kept asking, if the Earth is moving so fast through space, why don't we feel it? Why doesn't everything fly off into space? Galileo's brilliant insight was that motion is relative. When you're moving at a constant speed, you can't tell you're moving without looking outside. Drop a ball on a moving ship, and it falls straight down from your perspective, even though someone on shore would see it follow a curved path. For nearly 300 years, this understanding worked beautifully. Isaac Newton built his entire system of mechanics on these principles, and they predicted the motion of planets, the arc of cannonballs, the swing of pendulums. Everything made sense. Speeds added up according to simple arithmetic. If you're in a car going 50 kilometers per hour and you throw something forward at 20 kilometers per hour, an observer on the road sees it moving at 70 kilometers per hour. Perfect, clear, logical. But then, in the late 1800s, physicists started studying light more carefully, and things got weird. James Clerk Maxwell had just unified electricity and magnetism into a single theory, and his equations predicted that electromagnetic waves should travel at a specific speed, approximately 299, 792, 458 meters per second. We call this speed c, and we now know it as the speed of light. But here's what bothered physicists at the time. Maxwell's equations didn't say this was the speed relative to anything in particular. It was just the speed, period. This seemed impossible. Everything else in physics had speeds that were relative to something. The train's speed is measured relative to the ground. The ball's speed is measured relative to the train or the ground. But light speed, according to Maxwell's equations, was just this fixed number that popped out of the mathematics, apparently the same for all observers. Scientists couldn't accept this. They invented an invisible substance called the luminiferous ether that supposedly filled all of space. And they figured light must travel at this speed relative to the ether, just like sound travels at a specific speed relative to air. The Earth moves through this ether, they reasoned, so if we measure the speed of light in different directions, we should see different values depending on whether we're moving with or against the ether wind. In 1887, two American physicists, Albert Michelson and Edward Morley, conducted one of the most important failed experiments in history. They built an incredibly sensitive device called an interferometer that could detect tiny differences in the speed of light in different directions. They pointed it in every direction, tested it at different times of day and different seasons of the year when Earth's motion through space would be different. The result? Nothing. No difference whatsoever. Light traveled at exactly the same speed in every direction, regardless of how the Earth was moving. The experiment was so precise and so definitive that it couldn't be ignored. The ether theory was dead. But that created an even bigger mystery. How could light travel at the same speed for everyone, regardless of their motion? This is where the story gets truly mind-bending, and I want to know what you're thinking right now. Before we dive into what Einstein and Feynman revealed about this cosmic speed limit, pause for a moment and leave a comment. Do you think the speed of light being constant makes intuitive sense, or does it feel completely impossible? Have you ever wondered what would actually happen if you could somehow go faster than light? What do you think is really stopping objects with mass from reaching light speed? Is it energy? Is it time? Is it something else entirely? Share your thoughts in the comments because understanding your intuitions will make what comes next even more powerful. The resolution to this mystery that we're about to explore is one of the most beautiful pieces of reasoning in all of physics, and it fundamentally changed how we understand reality. Feynman had a special way of explaining this that cuts through the mathematics and gets right to the heart of why the universe works this way. So drop your comment now, and let's continue this journey into one of the deepest truths about our universe. Albert Einstein was a 26-year-old patent clerk in 1905. When he published a paper that would revolutionize physics, he did something that seemed almost absurdly simple, yet it required tremendous courage to do. He took the result of the Michelson-Morley experiment seriously. Instead of trying to explain away why light speed appeared constant, he simply accepted it as a fundamental postulate. The speed of light in vacuum is the same for all observers, regardless of their motion. Period. But accepting this one simple fact meant that something else had to give. If light travels at the same speed for everyone, and speeds don't add up the way we thought they did, then our understanding of space and time must be wrong. This was Einstein's breakthrough insight. Time and space are not absolute, universal quantities that tick away the same for everyone everywhere. They are flexible, malleable, relative to the observer's motion. This is special relativity, and it's one of the most counterintuitive yet experimentally verified theories in all of science. Here's where Feynman comes in with his characteristically brilliant way of explaining why you can't reach the speed of light. Feynman didn't just accept the equations of relativity. He wanted to understand them deeply, to see them from every possible angle, to make them intuitive, and he found a way to explain the cosmic speed limit that gets right to the heart of the matter. It comes down to energy and mass, and how they're related in ways Newton never imagined. In Newtonian physics, if you want to make something go faster, you add energy. The kinetic energy of a moving object is 1/2 its mass times its velocity squared. Double the velocity, you quadruple the energy. But you can always add more energy to go faster. There's no limit. In Newton's world, you can, in principle, accelerate forever. But Einstein showed that this equation is only an approximation that works at low speeds. The real relationship between energy and velocity is much stranger. As an object's speed approaches the speed of light, something bizarre happens to its mass. Not its rest mass, the mass you'd measure if the object were sitting still, but its relativistic mass, the effective mass that determines how hard it is to accelerate the object further. Feynman explained it this way. Imagine you're pushing a cart. At first, it's easy. A small push produces noticeable acceleration, but as the cart goes faster and faster, approaching the speed of light, it becomes harder and harder to accelerate. Not because of friction or air resistance, but because the cart's effective mass is increasing. The faster it goes, the more massive it becomes from your perspective, and the more energy you need to accelerate it further. At 90% the speed of light, the cart's effective mass has more than doubled. At 99% light speed, it's increased by a factor of about 7. At 99%, it's increased by a factor of more than 70. The pattern continues. The closer you get to light speed, the more the effective mass increases and the more energy you need to push even a tiny bit faster. This isn't a gradual increase, it's exponential. As you approach the speed of light, the effective mass approaches infinity. This is the key insight. To actually reach the speed of light, you would need infinite energy, not a lot of energy. Not the entire energy output of the sun or even the entire observable universe. Literally infinite energy. The universe is telling you, through the language of mathematics and the structure of space-time itself, that this is impossible. You cannot reach the speed of light if you have mass. But why? Why does mass increase with velocity? This is where Feynman's deep understanding really shines. The answer lies in understanding what mass actually is in the context of relativity. Mass isn't just a measure of how much stuff is in an object. It's a measure of an object's resistance to changes in motion, its inertia. And in relativity, inertia is intimately connected to energy. Einstein's most famous equation, E equals mc squared, tells us that mass and energy are equivalent, two forms of the same thing. An object at rest has rest energy equal to its mass times the speed of light squared. But when the object is moving, it also has kinetic energy, energy of motion. In special relativity, this kinetic energy doesn't just add to the object's total energy in the simple Newtonian way, it actually contributes to the object's effective mass. The faster you go, the more kinetic energy you have, and the more this energy contributes to your effective mass, making you harder to accelerate further. This creates a feedback loop. Adding energy to go faster increases your mass, which means you need more energy to accelerate the same amount, which increases your mass further, and so on. As you approach light speed, this feedback becomes so strong that additional energy barely changes your speed at all. Almost all the energy you add goes into increasing your mass rather than your velocity. Feynman loved to point out the experimental evidence for this. In particle accelerators like the Large Hadron Collider, physicists routinely accelerate protons to 99. 99991 the speed of light. At these speeds, the protons have so much kinetic energy that their effective mass is about 7,500 times their rest mass. These aren't theoretical calculations, they're measured facts. The accelerator's magnets have to be calibrated precisely for this increased mass to keep the protons on their circular path. If Newtonian physics were correct, the energies involved would have accelerated the protons to millions of times the speed of light. But they don't. They just make the protons heavier and heavier, exactly as Einstein predicted. Every single experiment, every particle accelerator, every high-speed cosmic ray detection confirms this. The speed of light is not just a barrier, it's a fundamental feature of how energy, mass, and velocity are related in our universe. But there's another layer to this that Feynman emphasized, and it might be the most important one. The speed of light isn't really about light at all. Light happens to travel at this speed because photons, the particles of light, have no mass. Anything with zero mass must travel at exactly the speed of light. It has no choice. The speed of light is really the speed of causality, the maximum speed at which information or influence can travel through space. Think about what this means. When you push on something, that push travels through the material at a finite speed, transmitted by electromagnetic forces between atoms. Those forces propagate at the speed of light. When you see something, photons travel from the object to your eye at the speed of light. When you think, electrical signals in your brain propagate at speeds far slower than light, but the fundamental electromagnetic interactions that make those signals possible are ultimately limited by light speed. Everything in the universe that involves cause and effect, one event influencing another, is limited by this cosmic speed limit. And here's the truly profound part. If you could go faster than light, you would violate causality itself. In special relativity, different observers moving at different speeds disagree about whether spatially separated events happen simultaneously. What one observer sees as happening at the same time, another observer moving relative to the first sees as happening at different times. This is called the relativity of simultaneity, and it's a direct consequence of the constant speed of light. Now, if you could travel faster than light, some observers would see you arriving at your destination before you left. From their perspective, you'd be traveling backward in time. This isn't science fiction or speculation. It follows directly from the mathematics of special relativity. Faster than light travel would allow you to create causal paradoxes, effects preceding causes, the whole logical structure of reality breaking down. The universe doesn't allow this. The speed of light isn't just a speed limit for objects, it's the speed at which cause and effect propagate, the speed at which information travels, the speed that maintains the causal structure of space-time. You can't outrun light because doing so would mean outrunning causality itself, and that would make the universe logically inconsistent. Feynman understood this deeply. In his lectures and books, he emphasized that the laws of physics aren't arbitrary rules imposed on the universe from outside. They're descriptions of how the universe actually is, patterns we've discovered through careful observation and clever reasoning. The cosmic speed limit isn't the universe being restrictive or limiting. It's a consequence of the deep structure of space-time, of how space and time are woven together into a unified fabric, where the speed of light is the conversion factor between time and space. 1 second of time corresponds to 299, 792, 458 meters of space in space-time. This is why the speed of light has the value it does. It's not a random number. It's the fundamental exchange rate between the dimensions of space-time itself. Feynman also loved to address a common question. What about things that do seem to go faster than light? Don't the galaxies at the edge of the observable universe recede from us faster than light due to the expansion of space? Yes, they do, but this doesn't violate special relativity. Special relativity says nothing can move through space faster than light. But space itself can expand at any rate. The galaxies aren't moving through space faster than light. The space between us and them is expanding. It's a subtle but crucial distinction. Similarly, you might have heard about quantum entanglement seeming to allow instant communication between particles. But this, too, doesn't violate the cosmic speed limit. While entangled particles have correlated properties, you can't use entanglement to send information faster than light. Every careful analysis of these supposed loopholes shows that the cosmic speed limit holds. Nothing with mass can reach light speed. No information can travel faster than light. No cause can influence an effect faster than light allows. Now let's talk about what this means for space travel and our cosmic neighborhood. The nearest star to our Sun, Proxima Centauri, is about 2 light-years away. This means light takes 2 years to travel from there to here. Even if we could build a spaceship that traveled at 99% the speed of light, which is far beyond anything remotely possible with current technology, it would take more than 4 years to reach that nearest star. The Milky Way galaxy is about 100 Fahrenheit light-years across. The nearest major galaxy, Andromeda, is about 5 million light-years away. The observable universe is about 93 billion light-years across. These aren't just big numbers. They represent fundamental limits on how quickly we can explore or communicate across cosmic distances. Even traveling at near light speed, which would require unimaginable amounts of energy, the universe remains vast, almost beyond comprehension. But there's a weird twist that Feynman also explained beautifully. While you can't go faster than light, strange things happen at time when you travel at speeds close to light speed. This is time dilation, another consequence of special relativity. The faster you move relative to another observer, the slower your clock ticks from that observer's perspective. From your own perspective in your spaceship, time passes normally. But if you travel to Proxima Centauri at 99% the speed of light, only about 7 months would pass for you, even though observers on Earth would see the journey take a bit over 4 years. Travel to the center of the galaxy at that speed, and from your perspective, the journey might take only a few years, even though tens of thousands of years would pass on Earth. This creates bizarre scenarios. You could, in principle, travel to distant parts of the galaxy and return within your lifetime, but everyone you knew on Earth would be long dead. You'd be traveling into Earth's future not by going faster than light, but by exploiting time dilation. Feynman pointed out that this is one of the most experimentally verified predictions of relativity. Muons, unstable particles created when cosmic rays hit the upper atmosphere, shouldn't reach the ground before decaying. Their lifetime is only about 2 microseconds, and even traveling at nearly light speed, they can only go about 660 meters before decaying. But the atmosphere is much thicker than that. Yet muons created 10 kilometers up routinely reach detectors at ground level. Why? Because from the muon's perspective, its lifetime is normal, but due to its high speed, space itself is contracted. The 10-kilometer journey is only a few hundred meters from the muon's perspective. From our perspective, the muon's clock runs slow due to time dilation, so it lives long enough to reach the ground. Same phenomenon, different perspectives, both correct. Every GPS satellite orbiting Earth has to account for relativistic effects. The satellites move fast enough and are far enough from Earth's gravitational field that their clocks run at a different rate than clocks on the ground. Without corrections for both special relativity due to their motion and general relativity due to being higher in Earth's gravitational field, GPS would accumulate errors of kilometers per day. The fact that GPS works precisely is yet another confirmation that these relativistic effects are real. Time really does flow at different rates for different observers. The speed of light really is constant for all observers. The cosmic speed limit really is fundamental. Feynman summarized all of this with characteristic clarity. The universe has a structure, a deep mathematical structure that connects space, time, matter, and energy. The speed of light isn't a random detail or an engineering limitation. It's a fundamental constant that falls out of this structure, as inevitable as the ratio of a circle's circumference to its diameter. You can't outrun light, for the same reason you can't make a circle with a different value of pi. It's not about trying hard enough or being clever enough. It's about what's logically possible given the way the universe actually is. And here's something beautiful that Feynman always emphasized. We only discovered these truths by paying careful attention to reality, by doing precise experiments like the Michelson-Morley measurement, by taking the results seriously, even when they contradicted our intuitions, and by following the mathematical logic wherever it led. Humans, living on a planet where nothing moves faster than a tiny fraction of light speed, managed to figure out the structure of space-time through pure reasoning and careful measurement. We discovered that our intuitions about time being universal and absolute were wrong. We found that space and time are part of a unified space-time fabric. We learned that mass and energy are equivalent. We understood that there's a cosmic speed limit built into the very structure of reality. None of this was obvious. All of it required letting go of cherished assumptions and accepting what the evidence showed us. That's the power of science, of systematic investigation of nature, of refusing to be satisfied with common-sense answers and instead demanding to understand how things actually work. The speed of light stands as a monument to this process. It's a reminder that the universe is under no obligation to match our intuitions, but it is comprehensible if we're willing to observe carefully, think clearly, and follow the evidence. You can't outrun light, but in trying to understand why, we've uncovered some of the deepest truths about reality itself. We've learned that space and time are not separate absolute things, but aspects of a unified space-time. We've learned that mass and energy are equivalent manifestations of the same thing. We've learned that causality has a speed, that the universe has a built-in speed limit that maintains logical consistency. And we've learned all of this not through mysticism or pure philosophy, but through the patient work of observation, measurement, hypothesis, and verification. Feynman's great gift was making these profound truths accessible, showing how they flow logically from simple observations and clear thinking. So the next time you see light, remember that you're witnessing the cosmic speed limit in action. Those photons are traveling at the fastest speed possible, the speed that nothing with mass can reach, the speed that sets the tempo for causality itself. The universe won't let you outrun light, because doing so would mean breaking the logical structure of space-time itself. And that's not a limitation, it's a feature, a fundamental aspect of the universe that makes cause and effect possible, that gives time its arrow, that allows the universe to make sense. That's what Feynman understood, and that's what he taught us. The cosmic speed limit isn't about what you can't do. It's about revealing what the universe actually is. So the next time you see light, remember that you're witnessing the cosmic speed limit in action. Those photons are traveling at the fastest speed possible, the speed that nothing with mass can reach, the speed that sets the tempo for causality itself. The universe won't let you outrun light because doing so would mean breaking the logical structure of space-time itself. And that's not a limitation. It's a feature, a fundamental aspect of the universe that makes cause and effect possible, that gives time its arrow, that allows the universe to make sense. That's what Feynman understood, and that's what he taught us. The cosmic speed limit isn't about what you can't do. It's about revealing what the universe actually is. But think about what this means for our place in the cosmos and our understanding of reality. We are beings made of matter, forever bound by this cosmic speed limit, living in a universe whose vast distances are measured in the time it takes light to cross them. When we look up at the night sky, we're not seeing the universe as it is right now. We're looking back in time. The light from distant stars took years, centuries, even millions of years to reach our eyes. We see the Andromeda Galaxy as it was, too, 5 million years ago, not as it is now. We observe the cosmic microwave background radiation from when the universe was only 380 Solarsiren years old, seeing photons that have been traveling through space for over 13 billion years. In a very real sense, there is no universal now that extends across the cosmos. Different parts of the universe exist in different moments depending on how we observe them, and this is directly because light takes time to travel, and nothing can go faster. This cosmic speed limit defines not just what we can do, but what we can know. There are regions of space so far away that their light will never reach us, because the expansion of space carries them away faster than light can travel through that expanding space. Not because anything is violating the speed limit, but because space itself is growing. These regions are forever beyond our reach, forever unknowable, not because of technological limitations, but because of the fundamental structure of the universe. We live in what cosmologists call our observable universe, a sphere centered on us with a radius of about 46 billion light-years. Beyond that horizon, there's more universe, perhaps infinitely more, but we can never see it, never interact with it, never know anything about it. The cosmic speed limit has drawn a boundary around what we can ever observe or influence. Feynman would say, this is humbling and beautiful at the same time. The universe is telling us about its limits and its structure, teaching us through the language of physical law what is possible and what isn't. Now here's something that Feynman particularly loved to emphasize. This cosmic speed limit, this impossible barrier that nothing with mass can cross, isn't cruel or arbitrary. It's necessary. Without it, the universe would be chaos. Imagine if there were no speed limit on causality. You could have effects happening before their causes from some observer's perspective. You could have logical contradictions, situations where event A causes event B, and event B causes event A, creating impossible loops in time. The universe would lack the logical consistency that allows it to have laws at all. The speed of light limit is what keeps reality coherent. It's what allows the universe to have a history, a sequence of cause and effect, a logical structure where the past influences the present and the present influences the future, but not the reverse. When you understand this, you realize that the cosmic speed limit isn't the universe saying no to us. It's the universe having a structure that makes sense, that allows patterns to exist, that makes science possible. And consider what this means about the nature of knowledge itself. Everything we know about the universe comes to us through signals traveling at or below the speed of light. Photons from distant galaxies, gravitational waves from colliding black holes, neutrinos from exploding stars, all of these messengers are bound by the cosmic speed limit. Our knowledge of the universe is fundamentally shaped by how fast information can travel. We build our picture of reality from light-speed limited signals, arranging them into a coherent understanding of space, time, matter, and energy. The fact that we've figured this out, that we've understood the cosmic speed limit and its implications despite living in a world where nothing moves faster than a tiny fraction of light speed, is extraordinary. We used careful reasoning, precise measurement, and mathematical insight to discover truths about the universe that are completely non-intuitive. Feynman once said that the paradox is only a conflict between reality and your feeling of what reality ought to be. We feel like speeds should add up simply. We feel like time should be absolute and universal. We feel like there shouldn't be a cosmic speed limit, but reality doesn't care about our feelings. The universe is what it is, and our job as thinking beings is to understand it as it actually is, not as we wish it to be. The cosmic speed limit is one of those places where reality defies our intuition completely, and yet it's absolutely, definitively, experimentally verified. Every particle accelerator, every GPS satellite, every cosmic ray detection, every observation of distant supernovas, all of it confirms that the speed of light is constant, that time dilation is real, that mass increases with velocity, that you cannot reach light speed if you have mass. This is the power of physics. This is the power of science. We don't get to choose what's true based on what feels right. We have to discover what's true by looking at reality, by measuring carefully, by testing our ideas against nature itself. And when nature tells us something that contradicts our intuition, we have to change our intuition, not reality. The cosmic speed limit forced us to abandon Newtonian absolute space and time. It forced us to accept that space and time are relative, that simultaneity is relative, that mass and energy are equivalent. It forced us to understand that the universe has a structure far stranger and more beautiful than anyone imagined.